Section: Introduction. In this section, we discuss the significance of transformers in deep learning, particularly their role in the success of large language models like GPT, Llama, and Mistral. However, we recognize that they struggle with generating very long sequences due to their slow performance and high computational demands. Recent linear RNN models, such as Mamba and GLA, have shown better performance than transformers in controlled settings for smaller tasks, although transformers still excel in larger applications. We observe that the training times for linear RNNs are comparable to those of optimized transformers, meaning that scaling either model requires considerable computational resources. The main advantage of linear RNNs is their faster inference speed, which is 5 times higher than that of transformers. This efficiency is crucial for applications that are currently limited by the large key-value cache of transformers, such as reasoning over lengthy documents and navigating extensive codebases. Additionally, workflows involving agents need large batch inference to explore more options and manage complex environments. To address these challenges, we aim to distill a large pre-trained transformer into a linear RNN for more efficient generation. We face 2 main technical challenges: mapping the weights from the transformer to the linear RNN and adapting effective transformer inference techniques, like speculative decoding, to our new architecture. Our contributions include demonstrating that we can reuse weights from attention layers to distill a large transformer into a hybrid linear RNN with minimal extra computation while maintaining much of its generation quality. We introduce a modified Mamba architecture that can be initialized directly from a pre-trained model's attention block. We also propose a multi-stage distillation process that combines progressive distillation, supervised fine-tuning, and directed preference optimization, resulting in improved performance compared to standard distillation. Furthermore, we develop a hardware-aware sampling algorithm and a fast decoding kernel for our Mamba and hybrid architectures, achieving a throughput of over 300 tokens per second for a Mamba 7B model. Our experiments show that we can effectively apply speculative decoding to our hybrid architecture. We successfully distill various large-scale chat models, like Zephyr 7B and Llama 3.8b, into linear RNNs using only 20 billion tokens for training. The results indicate that our distilled models perform comparably to the original models on standard benchmarks and even match or exceed the performance of similarly sized models trained from scratch on extensive datasets. Next, we explore the relationship between attention mechanisms and linear RNNs. We start by reviewing multi-head attention to clarify the shapes of the intermediate components, using explicit subscripts for sequence positions to highlight similarities between the 2 models. Attention is computed in parallel across multiple heads, each processing the sequence with a hidden size. Recent studies suggest that linear RNNs can compete with attention in large language models, and we note that various formulations of linear RNNs share similar structures. We acknowledge that linear RNNs have computational advantages over attention, particularly during training and inference. However, we also recognize that simply linearizing the attention formula can lead to poor results due to the loss of critical nonlinear characteristics. To enhance these models, we need to increase the capacity of the linear hidden state to better capture long-term dependencies, as previous work has shown that expanding the hidden state representation can improve performance. Section Summary. In this section, we discuss the limitations of transformers in long sequence generation due to their quadratic complexity and large KV cache requirements, while highlighting the advantages of linear RNN models, which offer faster inference. We propose a method to distill large pre-trained transformers into hybrid linear RNNs, demonstrating that this approach can maintain generation quality and improve throughput, ultimately achieving competitive performance on various language model benchmarks. Section: Distilling to an expanded linear RNN. In this section, we focus on creating an effective distilled linear RNN. Our goal is to closely align with the original transformer setup while efficiently expanding the linear RNN's capacity. Instead of trying to replicate the exact attention function, we start with a linearized version for distillation. We adapt the parameterization from Mamba to increase the hidden state size, initializing from the attention representation. Mamba employs a continuous time state space model to define a linear RNN using a differential equation. Here, we have a diagonal matrix for one part and continuous signals for others. To apply this to discrete time tasks like language modeling, we use a neural network to generate a sequence of sampling intervals and signal samples at those times. With these intervals and samples, Mamba approximates the continuous time equation through a linear RNN discretization. In the simplest case, this method recovers the linear attention to linear RNN conversion we discussed earlier. The advantage of Mamba is that with more parameters, it can learn richer functions without sacrificing efficiency. The only new parameters we introduce are the sampling rate and the dynamic matrix, which control the linear RNN through the discretization function, effectively increasing the hidden size. A key contribution of Mamba is its hardware-aware factorization, which combines discretization, state expansion, and linear RNN application into a single kernel. This approach avoids the inefficiencies of handling large parameters directly, allowing us to work with larger hidden sizes without significant performance costs. Next, we describe our full approach, which is outlined in an algorithm. This algorithm takes the standard query, key, and value heads from attention and feeds them into the Mamba discretization, followed by the linear RNN. This process initializes the model with linearized attention, enabling it to learn more complex interactions through the expanded hidden state. Our architecture replaces transformer attention heads with fine-tuned linear RNN layers while keeping the transformer MLP layers unchanged. We also handle additional components like grouped query attention, which shares keys and values across heads. Our architecture differs from many Mamba systems, which typically combine MLP SSM layers and use a single head. This initialization allows us to substitute any attention block with a linear RNN block. We experiment with hybrid models, retaining every few attention layers, and find that a stepwise replacement strategy is most effective. For knowledge distillation, we aim to train a smaller network that mimics a larger teacher network. After initializing from the transformer parameters, we focus on distilling the model to match the original language model's performance. We believe that most knowledge from the transformer is retained in the MLP layers, so we concentrate on the fine-tuning and alignment steps of the LLM while keeping the MLP layers frozen. In the supervised fine-tuning stage, we apply knowledge distillation to maximize the likelihood of a response given an input prompt. We have two common methods for distillation. One uses word-level KL divergence to match the student model's probability distribution to the teacher's, while the other, sequence-level knowledge distillation, replaces the ground truth text with the teacher's generated output. The second stage of instruction tuning aligns LLMs with user preferences. We use desired preference pairs to enhance the model's output, aiming to maximize a reward model while staying close to a reference model, typically the one after supervised fine-tuning. We can utilize the original teacher for distillation, defining a preference model based on a reward function. Previous research has often used reinforcement learning methods for this, but we find that direct preference optimization has been effective for optimizing this objective with direct gradient updates. Specifically, if we have preferred and dispreferred outputs for a prompt, we can reformulate the optimization problem and perform it at the sequence level by scoring these outputs and backprop aggregating to the student. To our knowledge, this is the first time DPO has been used as a distillation objective. Section Summary. In this section, we describe our approach to distilling a linear RNN from a transformer by adapting the Mamba parameterization to enhance the hidden state size while maintaining efficiency. We utilize knowledge distillation techniques to train the new model to replicate the original language model's performance, focusing on fine-tuning and aligning the model with user preferences through methods like sequence-level distillation and direct preference optimization. Section: Speculative decoding algorithms for linear RNNs. In this section, we explore speculative decoding algorithms for linear RNNs, aiming to enhance decoding efficiency. Both attention and linear RNNs face a challenge due to the serial dependency in autoregressive generation, which limits efficiency since systems must wait for previous tokens to be generated before proceeding. Speculative decoding offers a solution by using additional computational resources to predict future generations. We focus on applying this technique to large Mamba models, which can also benefit distilled models. We encounter challenges with RNN speculation, which involves two models, a draft model and a verification model. The draft model quickly generates potential future outputs, while the verification model checks if these outputs are the best choices at each step. The longer we can generate outputs before needing verification, the faster the overall process becomes. If a partial output matches, we can revert to the last successful point. Attention-based models are well suited for speculation because they can verify multiple tokens simultaneously, despite being slower in generation. In contrast, linear RNN models like Mamba perform differently, as their sequential decoding is already faster than attention. While Mamba has parallel modes for training, these are optimized for very long sequences and may not work well for shorter chains where conflicts are unpredictable. Another challenge is related to state caching in RNN models. In attention models, the state is represented by key-value caches, while RNNs use a single hidden state. To compete with attention, this hidden state must be quite large. During speculation, we need to revert to a previous state, which is straightforward for attention but requires caching all hidden states for RNNs, leading to significant memory overhead. To address these issues, we propose a new algorithm for linear RNN speculative decoding that utilizes hardware-aware multi-step generation. The core of our approach is a generation kernel that computes outputs and hidden states efficiently without overloading GPU memory. This kernel allows us to save the state before evaluating draft tokens, enabling us to recompute the correct state quickly if a token is rejected. We assume that memory is the bottleneck in decoding, allowing us to compute multiple steps with minimal overhead compared to single-step decoding. Our algorithm maintains only one hidden state in cache for verification and updates it based on the success of the multi-step kernel. Additionally, we extend speculative decoding to hybrid architectures that combine RNN and transformer layers, where RNN layers handle verification while transformers perform parallel checks. If the draft model is a Mamba or hybrid, the speculation process becomes more complex, as the draft model must recompute the state for accepted tokens from the previous iteration. To validate our approach, we test speculation using Mamba 7b and Mamba 2.8b as target models, with results presented in our tables and figures illustrating the performance of the multi-step kernel. Section Summary. In this section, we explore speculative decoding algorithms for linear RNNs to enhance decoding efficiency by utilizing a draft model for generating potential completions and a verification model for checking their validity. We propose a hardware-aware multi-step generation approach that minimizes memory overhead while allowing for efficient state management during speculation, particularly in hybrid architectures that combine RNN and attention layers. Section: Speedup on H100 GPS. In this section, we discuss the performance of our algorithm on H100 GPS. Our initial implementation shows good results on Ampere GPUs, but we face more challenges with H100 GPS due to the faster GEM operations, which highlight the overhead from caching and recomputation. While our naive implementation achieves a speedup of 1.5 times on 3090 GPUs for the Mamba 2.8b model with a 60% acceptance rate, it does not show any speedup on H100s. To improve performance, we optimized our implementation by combining kernel operations and enabling easier caching and recomputation of previous steps. Specifically, the verifier model now includes recomputation from the cache, multi-step decoding for new draft tokens, and caching within a single kernel. Similarly, for the draft model, we also fuse recomputation, decoding, and caching into one kernel. These enhancements lead to speedups on H100 GPS. For our experiments, we use two large language model chat models, Zephyr 7b, a fine-tuned version of Mistral 7b, and Llama 3 Instruct 8B. We also utilize hybrid versions of Mamba and Mamba 2 with varying attention layers, referring to the model with no attention layers as pure Mamba. Mamba 2 is designed for newer GPU architectures, while Zephyr Mamba and Llama 3 Mamba indicate distillations from Zephyr and Llama 3 Instruct 8B, respectively. In terms of training, we employ a three-stage distillation process that does not require pre-training data. In the first stage, we generate pseudo-labels using ultra-chat and ultra-feedback as seed prompts. The student model is trained for one epoch with specific loss parameters. We use the Atom W optimizer and a linear learning rate warm-up followed by cosine annealing. The second stage involves supervised fine-tuning on various datasets, while the final stage includes distilled alignment for models from Zephyr and LLaMA3. We compare our models against various baselines, including pure and hybrid linear RNN models. For evaluation, we use single-turn and multi-turn chat benchmarks to assess our model's performance in following instructions and responding to prompts. Our distilled hybrid Mamba model, 50%, performs comparably to the teacher model in the MT benchmark and slightly better in the Alpaca eval benchmark. The performance of the distilled hybrid models with fewer attention layers is slightly lower than the teacher models in the MT benchmark but still outperforms some larger transformers in Alpaca eval. However, the distilled pure model shows a significant drop in accuracy. Notably, our distilled hybrid model outperforms Falcon Mamba, which was trained from scratch with a larger dataset. Section Summary. In this section, we discuss the challenges and optimizations of our algorithm on H100 GPUs, highlighting that while a naive implementation shows decent speedup on 3090 GPUs, it initially fails on H100s due to faster GEM operations. We then describe our optimized implementation, which fuses kernel operations and enhances caching and recomputation, resulting in improved performance on H100s, and outline our experimental setup and evaluation of various models against chat benchmarks. Section: Evaluation on general benchmarks. In this section, we evaluate our models on various general benchmarks. For the zero-shot evaluation, we use the open-source LM evaluation harness library to assess 10 tasks, focusing on metrics like accuracy for Wino Grande, PIQA, Hella Swag, Arc Easy, Arc Challenge, MMLU, OpenBook QA, Truthful QA, PubMed QA, and Race. We analyze the probabilities assigned by our model to each answer choice. Our results, shown in a table, indicate that both the hybrid Mamba Llama 3 and Mamba 2 Llama 3 models, which are distilled from the Llama 3 Instruct 8B, outperform the Tri-Mamba and NVIDIA Mamba models that were trained from scratch. We notice that performance decreases with more linear RNN layers, but remains competitive at 25% compared to models trained from scratch. For benchmark evaluation, we also report few-shot evaluations on the OpenLLM leaderboard, conducting 25 shots on Arc Challenge, 10 shots on Hella Swag, 5 shots on MMLU, and 5 shots on Winagrande. For GSM-8K, we follow the evaluation for instruct-tuned models, which is designed for chat models, and include the Crux benchmark for evaluating reasoning on code. All models are evaluated using greedy decoding. Our distilled hybrid models perform similarly to the best open-source linear RNN models on the OpenLLM leaderboard, while surpassing their corresponding open-source instruct models in GSM-8K and Crux. In our setup, we perform speculative decoding with the distilled hybrid models, running experiments with both hybrid Mamba at 50% and 25% as our main models. We train 2 and 4 layer transformer draft models on the 2.5 dataset for about 3 full epochs, using a shrink and fine-tune approach. We initialize the draft layers from the Zephyr 7B model and apply loss masking to focus on next token prediction loss from the training set. Our speculative decoding experiments are conducted on a single NVIDIA RTX 3090. The results show that our hybrid speculative decoding, using both Zephyr and Llama hybrid models, achieves speedups of over 1.8 times on the Zephyr hybrid compared to the non-speculative baseline. The 4-layer draft model we trained has a higher acceptance rate but incurs some additional overhead due to its size. For the Llama hybrid models, the speedups are more modest because of the larger draft model size. We also compare our distillation approach with others, noting that removing more layers leads to worse performance. Our method shows smaller degradation in perplexity compared to a previous baseline that distilled a transformer model into a hyena model using a different progressive knowledge transfer approach. In related work, attention-free models are gaining popularity for their efficiency in language processing tasks. Models like S4 and its variants have shown good results in long-range tasks. Gated SSM architectures incorporate gating mechanisms for language modeling. The Mamba model suggests that static dynamics in these methods may not effectively handle input-specific context, which is important for language modeling. Mamba has been shown to outperform transformers across various sizes. There have been few attempts to distill into linear RNN models, with some approaches focusing on constant time inference. Speculative decoding has emerged as a method to speed up inference in large language models, particularly transformers. This technique uses a smaller draft model to generate candidate tokens, which the larger model then verifies. Some studies have proposed methods to improve inference quality and efficiency in this process. Section Summary. In this section, we evaluate our models using various benchmarks, demonstrating that our distilled hybrid models outperform existing open-source models in zero-shot and few-shot settings. We also explore speculative decoding techniques, achieving significant speedups while maintaining competitive performance, and compare our distillation approach to others, highlighting its advantages in perplexity reduction. Section: Limitations. In this section, we acknowledge a potential limitation of our study. Our evaluation focused mainly on large-scale language models, specifically those in the 7 billion to 9 billion parameter range. This raises questions about whether our method would work as well on smaller models. While larger models have shown impressive performance improvements, we have not fully examined how our approach applies to smaller, more computationally efficient models. We suggest that future research should explore our method's effectiveness on smaller transformer models. This could involve training these models from the ground up and using distillation techniques to evaluate their performance across different metrics. Such investigations would help us better understand the generalizability and limitations of our approach.